We're going to analyse and complete tasks that are related to the intersection of lines if we're given position vectors. And we're going to link back to stuff we've learned earlier when we did some two-dimensional work. So in two space, we've got lines that can intersect at a point. We've got other lines that are parallel. We've got other situations where the lines coincide. Now, coincide is basically the opposite to the word distinct. So it's an antonym. Okay, so if lines are distinct, you can clearly tell that they're two different entities, but coincide is sort of the opposite of that. Let us extend on this now into 3 dimensions and into some further refinement of these ideas, especially involving position vectors. Let's consider this case here. We've got two lines, L1, and we've got line L2, and they've got position vectors that describe them. We can see that these are clearly parallel. We can see that by looking at the direction vector part of the equation, and we have I minus j here and 2i minus 2j. So due to the existence of a scalar multiple, we have lines that are clearly parallel. But do they coincide? So that means one subsumes another one. Are they, basically the same line? Or are they distinct? One way of looking at that is getting the position vector from one of the two given lines, like I've just highlighted there, and ask yourself, does this exist on L1? And when I say it, I should clarify that the point that is at the end of that position vector. So we're looking at the point 2, 3. Does it exist on the first line? If the point does not exist, well, they can't coincide. They can't be one and the same. So I'm going to write R1 in a form where it's easier to see the I and j components. So from above, R1 is 2 plus lambda I plus 2 minus lambda j, where lambda is any real number. And we have to see if there's a solution such that we can get 2i plus 3j. If there is a solution, there is a point. But if there's no solution, that rules out whether they're coincident or not. So looking at each separate part, looking at the I components, 2 plus lambda equals 2, so lambda would have to equal 0. But using the j components, 2 minus lambda equals 3. So we would have lambda equals -1, and that's inconsistent. So there's no solution to that. And there's therefore they're not coincident. They don't coincide. What that means then, therefore, the ultimate conclusion is yes, they're still parallel, but distinct. Okay, so the regular parallel lines, They're not coincident, they're distinct parallel lines. That's a conclusion we can draw from that. Another task we might do that's related to these ideas is find the position vector of the point of intersection of these lines. So intersection, and when we find that intersection, we need to find the position vector that describes that point. So, as we have with other work that's prior to learning about vectors, the point of intersection, we make the two entities equal to each other. So at the point of intersection, POI, we have R1 equal R2. That solution, that situation will describe the point of intersection. So we have two. Now I'm going to also write these vectors in a more convenient form, just like I did before. So we have 2 plus lambda. Now lambda and mu are both parameters. Okay, so we've seen parameter t before, and maybe parameter k. These are just some parameter, okay, which take the values of real numbers. So we have 2 plus alpha I. We have 2 minus alpha j equaling, now we have 3 mu I plus -1 2 mu j on the other side there. And clearly these are not parallel lines because you don't see any scalar multiple in terms of the direction vectors. So that's a good sign. So let's get to work. So what we have is to equate parts. So equating components. So for, in terms of I component, we have 2 plus lambda equaling 3 mu. So lambda equals 3 mu, take 2. Now by the way, this line here, if I didn't write this in, I could have left it like that, and then I could subtract this equation with the one I'm about to generate, or I could keep going and end up with this line here and use substitution, because we're going to use simultaneous equations. We have our second equation there, and I've just labelled the equations. So we can then come up with, by subbing 1a into 2, so we can go 2 minus, where lambda is, we can replace it with 3 mu minus 2. So this is one way of doing it. There are other ways. So we have 4 minus 3 mu equals -1 minus 2 mu. So now I'm adding 1 and adding 3 mu to both sides. I've realised an error. I've had to go back a couple of steps. I'm going to actually just go, I've reversed a couple of those last lines there. I'm actually just going to go 1 plus 2, and so on the left hand side we'll have 4, and on the right hand side we'll have -1 plus mu. Sorry, -1. By the way, the mistake came from, I wrote earlier on, I wrote a minus there that should be a plus. That's why I've had to make a sudden change. So we then get 4 equals -1 plus 5 mu. From that we can easily see that mu equals 1, and by substitution into one of the original equations we can also ascertain that lambda equals 1. I'm not going to show that bit to save some time. So what you can do, you've got a choice, or if you want to be really sure you could use both, but you sub those values in and you'll get the position vector. Perhaps you'd like to just sub 1 in, like mu into the original equation that involves mu, which is R2. Alright, you could try putting that in there and see if mu matches if you were to put in lambda for there. So it's like a way of confirming it. Okay, so I'll just show subbing mu equals 1 into R2 and see what we get. And either way, whether you use mu or lambda, or as I said, you could confirm you get 3i plus j. So the point, that means the conclusion here, important to actually write down, point of intersection has position vector (3i plus j).